All right, this is section 4.4 and 6.6. They're combined together in this lesson. We're going to be solving quadratic and higher order inequalities. In this section, we're going to talk about quadratic inequalities, polynomial inequalities, and we're going to solve them algebraically and with graphical methods, so you'll need your calculator. Okay, in the first set of problems that we're going to do in this lesson, you can see there's a polynomial graphed already, and we're going to find the values of x from the graph that satisfy the given condition. We're going to write our answer in inequality form with greater than and less than symbols, and then we'll also practice writing it in interval notation, and you're going to have to kind of flip-flop back between those as you're doing your homework, so make sure you're really careful when you read the instructions in my math lab on this lesson. In the first problem, we're finding when this function f of x is less than 0, which is just a fancy way of saying when are my y values, because that's what f of x means, negative. And my y values will be negative anytime that my graph falls below the x-axis. So a lot of times when we're going to look at these problems today, we're going to focus on the x-axis and either being above it or below it, because that makes my function greater than or less than 0. We're always going to see a 0 on that other side, and if we don't, we're going to create that 0 when we solve algebraically. So this function is negative, less than 0 on this part of the graph, and then on this part of the graph as well. So now we want to list the x values where that happens at. So these x values, think about this kind of like when we did increasing, decreasing, and constant before. The x values from -6, I can see that is where it touches my x-axis, and then everything lower than that, -7, -8, and we're assuming there's an arrow on there. So all x values less than -6, we're not going to include -6 because -6 is where it's equal to 0. And then it also is below the x-axis between the x values of -2 and the x value of 4. So we're going to write that as -2 less than or equal to x, less than or equal to 4. And again, I don't need those equal signs because that's where it's equal to 0, and we just want something strictly less than 0. So this is how we would write it with inequalities in inequality form. You might see that worded. Now, if we want to write this in interval notation, it would look like the following. -infinity to -6, our union symbol to connect, and then -2 to 4. And again, that's all the x values where this graph is below the x-axis. Okay, let's look at the next one. Here we want to know when my function, my y values, are greater than or equal to 0. So here we're looking for them to be positive. So the parts of this graph that are above the x-axis are here, here, and here. And again, we're assuming there's arrows on either side of that. So to list those in inequality form, we would say all of our x values less than -3, and this time we're going to include -3 because my inequality says they can be greater than or equal to. Then in the middle, any x value between -1 and +1 would give me a positive y value. And then finally, any x value greater than or equal to 3 would give me a positive y value or a value at 0. Putting that in interval notation, we say -infinity to -3. This time, because we can equal 0, we use a bracket. -1 to 1, and then 3 to infinity. I personally prefer the interval notation. I think it looks a little bit cleaner than all the inequality signs, but you can also do that as well. Sometimes you'll even see the word and or show up between these if you see it written out. Okay, here are a couple for you to try. In problem number 3, you're finding where the function is strictly greater than 0. And in problem number 4, you're finding when the function is less than or equal to 0. For number 3, you're going to write your answer as an inequality, just with your greater than, less than symbols. For number 4, you're going to write your answer with interval notation. Okay, so in number 3, we want to know where our y values are greater than 0, so strictly the positives are what we're looking for here. So that would be this little hill here, and then this hill here. You are not including 1 because 1 is where it's exactly equal to 0. We only want the positive. Same with -2. We're not going to include -2. So writing that as an inequality, it would look like -2 less than, I always want to put that equal sign there, just strictly less than x less than 1. Inequalities should always point in the same direction at the smaller number. And also x values greater than 1. For number 4, we want when our y's are less than or equal to 0. So this time we're looking for negatives, and we can include 0 as well. So that's this portion of the graph, these portions of the graph here, and then everything else is above the x-axis. Putting that in interval notation, it would look like -infinity to -4, including -4, because I can include 0 here. So that says that every x value smaller than -4 will give me a y value below the x-axis. And then everything between -2 and 3 as well. We don't have any breaks here because that's a continuous interval, and every value on that interval is less than 0, so negative or equal to 0. So we're going to say -2 all the way to 3, and again, everything there is a bracket because my inequality sign said equal to. Okay, so now kind of the big idea. Most of the problems that you're going to do in this lesson, you're not given the graph, you're instead given an equation, and you're solving algebraically. So we're going to kind of work our way up here. We're going to start with quadratics, powers of 2, and then we'll do some cubics and some quartics, and we'll see what happens as they get larger. But the procedure for all of them is going to be the same. In your first step, you're going to move all terms to one side, and we're going to do this first problem together as we run through the steps so you can see what each of these look like. So this problem, this inequality, already has 0 on one side. If it didn't, I would have to shift everything over. You may have to reorder some terms as well. Remember, it's always really nice to have your powers in descending order, exponents highest to lowest. Then you're going to factor your polynomial. So that could look different depending on what kind of problem you have. You might factor by grouping. You might factor out a common monomial, something you have in common. This problem, I have a trinomial, 3 terms, and a 1 in front of my x squared. So this is where we can factor into 2 binomials, 2 sets of parentheses. And you're looking for 2 numbers that multiply to the last value and add to the middle value. So what multiplies to -6 and adds to -5 are -6 and +1. And I'm just going to bring my inequality sign down. Then we're going to find the roots. So roots are what we've done before, where we use our zero product property. We set each of our factors equal to 0 and we solve. We get 6 and -1 in this case. Instead of those being actual solutions here now, because instead of wanting to know when this function is equal to 0, we want to know when it's greater than or equal to 0, we're going to, instead of calling these roots, we're going to call them breaking points. And we're going to use them to divide up our number line into segments. So we know this is going to be the graph of a quadratic. If you looked at this graph right now, -1 and 6 would be where it's crossing the x-axis. So what we need to figure out is when it crosses, where is it above and where is it below? Because that's going to tell us where it's positive and where it's negative. To do that, in step 4, we're going to use what we call test points. Test points are numbers that we're plugging in that are in each of these intervals. And you can pick any x value in this interval. So I'm just going to choose some easy ones, -2, 0, and 7. Okay, but again, any x value within that range of numbers would work. To test the values, you're just going to plug those numbers into the function. So if I plugged -2 in, it would be -2 squared minus 5 times -2 minus 6. And you can use your calculator to simplify this if you need to. It's going to be 4 plus 10, which would give me 14, minus 6, which would give me 8. Now, the number itself is not super important here. Remember, what we're trying to figure out is it above the x-axis or below the x-axis. And 8 is a positive number. So that tells me, in general, if I plug any number in this interval, I'm going to get a positive number. And on that part of the graph, it's above the x-axis. So now we're going to do the same thing. We're just going to plug in 0 and 7. Let's say I plug in 0. 0 squared gives me 0. 5 times 0 is 0. Minus 6 gives me -6. But more importantly, it's a negative number. And then finally, we'll plug in 7. Need my eraser here. If I plug 7 into this function, 7 squared minus 5 times 7 minus 6. So 7 squared is 49. Then I'll have minus 35, which is 14. Minus 6, again, gives me 8. So more importantly, I get a positive number out when I plug that value in. Okay, so now to answer the question, once you've got your number line filled out with your pluses and minuses, you can then determine where your function is positive above the x-axis or negative below the x-axis. In this problem, we wanted to know when our quadratic was greater than or equal to 0. So when it was positive or equal to 0. So that would be this interval and this interval. And remember, -1 and 6 are included in the interval here because that's where it equals 0. So that's part of my solution. So I like putting in an interval notation. In interval notation, I think it follows really nicely with the inequalities, -infinity to -1. -1's included, so I use a bracket, and then 6 to infinity. And if you wanted to check this, you could graph the function in your calculator and see that those portions of the graph are where it's above the x-axis. If you wanted to put it in inequality form, it would be all x values less than or equal to -1 and or whatever you want to say. And sometimes my math level just have you put a comma between these even. X values greater than or equal to 6 would be the other set. Okay, so now let's practice this process. Here's another quadratic inequality. First step, remember, get it compared to 0. It's already compared to 0 for me. Second step is to factor. So I do have a number in front of the x squared. It doesn't look like any of my terms have anything in common. I don't have 4 terms, so I can't use grouping. This is the method where, I guess technically it's called grouping. You create the grouping situation. When a is not equal to 1, you bring down your first and your last term. You multiply those together. In this case, I get -18. Then we're trying to find 2 numbers to split our 7x into that multiply to -18 and add to 7. So what multiplies to -18 and adds to 7? Those numbers are +9 and -2. And we're going to attach an x to each of those. And now I can factor by grouping. So I'm going to pair up my first 2 terms. They have a 3x in common. That leaves me with x plus 3. My next pair of terms, they have a -2 in common. Also leaves me with x plus 3, and that's how you know you're doing it right. 3x minus 2, what I factored out, is one of my factors. X plus 3, what I was left with both times, remember those should match, is your other factor. If you set each of those equal to 0, you will get +2/3 and -3 as a solution. Those now, instead of final answers, are breaking points on our number line. -3 and 2/3. We're going to pick test points in each group of numbers. So I'll pick like -4 here. 0 is always an easy one. 1's always pretty easy as well. And I'm just going to kind of do this quick mentally, but you can absolutely plug them in your calculator. Be careful with the negative numbers. Make sure you put the negative in parentheses. So if I plug -4 in, -4 squared is 16 times 3 is -48. Plus 7 times -4 is -28. So I would have, oops, sorry, I think I have a 48 and a -28. So that gives me 20 minus 6 is 14, which gives me a positive number. That's what's important here. If I plug in 0, that one's quick. The first 2 terms disappear. -6, I get a negative. And if I plug in 1, my first term is going to be 1. My second term is going to be 3 and 7, which is 10. -6 gives me 4, which is positive. See what happens when I do it mentally? You might want to use your calculator. Here we're looking for when the function is less than 0. So this time we want negative values, and we are not going to include our breaking points because our breaking points are when it's equal to 0, and we want values that are strictly less than, strictly negative. So that would only include this group of numbers, and again, it does not include my breaking points. So in interval notation, my answer is -3 to 2/3. If I put that in the inequality form, it would be -3 less than x less than 2/3. Inequality symbols always point in the same direction at the smaller number. Again, if you want to check it, graph this in your calculator and see if between those two values on your x-axis is when your parabola is negative, when your y values are negative. Okay, let's try another one. I'm not going to continue to put all the answers in both notations. I'm just going to stick with interval notation from now on, but you can always practice if you want on your own, putting it in both notations to prepare for your My Math Lab homework. Okay, so in this example, 5x squared plus 6 greater than equal to 13x, not equal to 0 here. So I'm going to move everything over to the left first to set up my problem. I'm going to subtract 13x to move it over, and I'm going to put that in the middle because I like my powers to be in descending order. Now this is one that you can factor. If that last problem was a little bit of much with the factoring for you, I'm going to tell you you can use the quadratic formula for these, and the quadratic formula will take you straight to those breaking points. So if you prefer, especially when the factoring gets a little nasty with that number in front of the x squared, to use a quadratic formula, if you're confident with that, go for it. We'll do that in this problem. So x equals opposite of b, 13, plus and minus square root b squared, 13 squared is 169, minus 4 times a times c, all over 2a, 2 times 5. I need to simplify underneath my square root. So 169 minus, that'll be 120, so I'll have a 49 under there. In the denominator, I have a 10. Square root of 49, that's a nice, pretty perfect square, gives me 7. And then I can simplify once with the plus and once with the minus, and that's going to give me my two breaking points that go on my number line. If I simplify with the plus, 13 plus 7 gives me 20, divided by 10 gives me 2. If I simplify with the minus, 13 minus 7 gives me 6 over 10. 6 over 10 reduces to 3/5. And now I have my breaking points. Those are the same answers you would get if you factored the quadratic and set each factor equal to 0. So it's up to you which way you want to do that. It's just the path of least resistance and whatever you feel more confident with, really. Okay, breaking points here. I'm going to pick 0, 1, and 3 as my test points. We're plugging it into the equation that is compared to 0. So I'm plugging into this line right here. If I plug 0 in, the first two terms will be 0 and the last term will be 6. More importantly, it is positive. If I plug 1 in, I'll have 5 minus 13, which is -8, plus 6, which is -2. More importantly, I get a negative number. And if I plug in 3, my first term will be 3 squared 9 times 5, which is 45, minus 13 times 3, which is 39. So 45 minus 39, let's see, gives me 6, plus 6 gives me 12. I get a positive number. And it looks like in the last few problems we've gotten kind of the same pattern over and over again. That is not necessarily always the case, so don't make a rule of that. Here we are looking for when this quadratic is greater than or equal to 0. We're looking always where it's compared to 0. So here we're looking for the positive values, which are here and here. Because it's greater than or equal to, we include our breaking points in our answer. So -infinity to 3/5, the bracket, and then 2 to infinity, 2 also has a bracket. Okay, let's look at an application problem now of quadratic inequalities. So this problem says, if a rocket is propelled upward from ground level, its height h in meters after t seconds, so again, make sure you know what those variables stand for, it might make things later better a little later on, is given by the following function. H of t equals -9.8 t squared plus 98 t. During what interval of time will the rocket be higher than 235.2 meters? So that's my height. So 235.2, but it's not going to be equal to here. We want my height to be greater than, higher than 235.2. So negative 9.8 t squared plus 98t. And I think I wrote my inequality sign backwards there. We want the height that we have to be greater than 235.2. There we go. So this is the height we're calculating. Okay. All right. So again, we want to get it compared to 0 first. So I'm going to move that 235.2 over. Negative 9.8t squared plus 98t. And then I'll subtract negative 235.2. Okay, and it looks like I could maybe try to factor this, but this might get a little gross, so I think I'm just gonna, well, I wonder if 235.2, I could factor a negative 9.8. Let's see if that divides in evenly. 235.2 divided by 9.8. Ooh, that does work out evenly. I'm gonna take out that common factor here. That leaves me with t squared. If I do 98 divided by negative 9.8, I get negative 10. And if I do negative 235.2 divided by negative 9.8, I get positive 24. And this guy is pretty easy to solve now because I don't have a number in front of my t squared. Now, if you didn't see that because these numbers were a little nasty, you can always just go straight to the quadratic formula if you feel stuck on those. All right, so because I don't have a number in front of the t squared, I'm just looking for two values that multiply to 24 and add to negative 10. So negative 9.8. Numbers that multiply to positive 24 add to negative 10 must be a negative 4 and a negative 6. And then if I set each of those equal to 0, I get 4 and 6. So what do those values mean? Those values mean after 4 seconds and 6 seconds, that's when the rocket hits exactly 235.2 meters. So it hits 235 on the way up, 4 seconds after it's been in the air, and 235 on the way down 6 seconds after it's been in the air. So we want to know what interval of time will it be higher than that. It's going to be between those two values because it's rising and falling if we follow the path of a rocket. Okay, and you can kind of imagine what this picture would look like even without putting it in your calculator. 235.2 is going to look something like this. 235.2, and then this is after 4 seconds. And this is after 6 seconds. So between 4 and 6 seconds is when it's above that height. Now, if you're not sure about that, if you can't kind of picture that piece in your mind, you can make your number line as we did with those other problems. Put a 4 and a 6, and you're going to see negative, positive, negative. And again, we want to know when it's greater than, when it's positive. So we're going to use those values between. Okay, here is a quadratic for you to try. Put your answer in interval notation. All right, so you need to get this compared to 0 first. So I'm going to subtract 8x and put it in the middle to keep my terms in descending order. This one you should have factored pretty easily. Two numbers that multiply to 7 and add to negative 8 are negative 1 and negative 7. If you set each of those equal to 0, you will get positive 1 and positive 7 as roots or breaking points. Number line at 1 and 7. If you plugged in a number smaller than 1, you should get a positive number. If you plugged in a number between 1 and 7, so like 2, for example, you could use, you're going to get a negative number. And if you plug in a number larger than 7, you're going to get a positive number. And you could have picked any numbers. If I were doing it, I'd probably pick like 0. Again, 0 is super easy to plug in. 2 and 8. Don't make it crazy. From there, in this problem, you guys were looking for where it is greater than 0, so anything that's positive, but not including our breaking points because we're not equal to here. So we're including this interval and this interval. In interval notation, that would be negative infinity to 1 and 7 to infinity. Okay, and the next problem we're going to solve with technology. And I'll show you how you can use technology to help you, especially when they become more difficult with the quadratic formula or factoring. Before we get to the technology, though, the first thing we're going to do is we're going to get this equal to 0. So I'm going to move everything to one side. I'm going to move everything over to the left, maybe. So 3x squared plus 4x minus 8 greater than or equal to 0, because I have to add 4x and subtract 8 to get it over to that left side. Okay, now this is what we're going to put in our calculator. So let me get my calculator up here. Here we go. Okay, in y equals, we're just putting in 3x squared plus 4x minus 8. And then I'm just going to graph it in the standard window, so zoom 6. Okay, and then this is just like the pictures we were looking at the very beginning of this lesson. We want to know, where is this function greater than or equal to 0? And you can see there's two parts of the graph. This part of the graph and this part of the graph are greater than above the x-axis. So the question is, where are we hitting the x-axis? It doesn't look like we're hitting at a nice pretty number. So we're going to have to calculate that, and we've done that before. To calculate it, we're going to hit second, trace, that's our calculate menu. And remember, another word for x-intercept is 0, so we're going to calculate the zeros. Number 2. Now my first 0 looks like it's occurring between -2 and -3. So that's what I'm going to use for my left bound and right bound. My left bound is -3, my right bound is -2, and then guess. And that's my first 0, or my first breaking point. Okay, we can do it again. Oop, wrong one. There we go. Okay, my other 0 looks like it's maybe at 1, maybe a little to the right of 1. I'm going to use left bound and right bound of 0 and 2 for this next one. So second, calculate, maybe, 0, number 2. So I'm going to use a left bound of 0 and a right bound of 2. Okay, and we're calculating this x-intercept right here. We'll hit guess. And there is my other 0, my other breaking point. Come on, go down there. There we go. Okay. So now we have this picture. Let me get my pens back. There we are. And in this portion of the graph and this portion of the graph, we're above the x-axis. And we have zeros, and let's round to 3 decimal places. So this first 0 is at -2.431. And this other 0 is what we calculated on this guy, which is, if I round to 3 decimal places, 1.097. So all x values less than that -2.4 and all x values greater than that 1.097 are my solution. And then we also will include our breaking points because my inequality sign says greater than or equal to. So our final answer here is going to be -infinity to -2.431 with a bracket. So that's this first side. Then my union symbol. To find the second side, we use the other breaking point, 1.097. Again, I use a bracket because that's where it's equal to 0 at. And then all the way to infinity. So if a problem says to solve using graphical methods, you're probably going to get numbers like this that are difficult to get with the quadratic form. Well, you can get it with the quadratic formula, but there's going to be some simplifying. Definitely not something you can get by factoring or using a root method, though. And then this is also a great strategy to use just to check your answer. So we kind of see this picture. We can calculate those zeros. You can use this for any of those previous problems as well if it's something that you get stuck on. Okay, let's try a cubic problem. So strategy is similar at the beginning here. We're going to get it all compared to 0. So I'm going to move everything over to the left, x cubed minus x squared less than or equal to 0. Then here, it looks like I have some things in common that I can factor out of both of my terms. So I'm going to take an x squared out of both terms, and that will leave me with x minus 1. Remember, you want, when you factor something out, to be able to distribute what you factored out back in and be right back where you started. Less than or equal to 0. Now I can set my factors equal to 0. If I set x squared equal to 0, I just get 0. If I set x minus 1 equal to 0, I get 1. So there are my breaking points at 0 and 1. And we're going to plug in test values between each point. So I'm going to use -1, 0.5, and 2. And I'll just pull up my calculator and do this with you this time. So I've got it out. Okay, so I'm just going to go to my home screen, second mode, to get back to your home screen. And again, I'm plugging it in to where it's compared to 0. So x to the third minus x squared. That's the calculation we're doing. So -1 to the third minus -1 squared. And that gives me -2. So it's a negative number. We'll fill that in a minute. If I plug in 0.5 to the third minus 0.5 squared. And I get, again, a negative, -0.125 here. And let's do it one more time with 2 to the third minus 2 squared. Notice I'm just putting everything in parentheses each time. Parentheses are never going to hurt you when you're plugging this stuff in. And I get a positive. So when I plugged my values in, I got negative, negative, positive. So let's go ahead and fill that in. All right, I want to know when my inequality is less than or equal to 0, so that means I'm looking for negative values here. So that's this interval and this interval. I also want values that are equal to 0, so I am going to include this breaking point and this breaking point. Now you can list this in 2 separate intervals if you want to, but because every value less than 1 is actually included, we can just say -infinity to 1 with a bracket. If you said -infinity to 0 and then 0 to 1, this is equivalent, but it's not the simplest version that you can write it in because 0 is included in both of those intervals. So more than likely, if you put something like that in my math lab, it will be marked wrong. So just be careful. Now, if 0 was not included, if we had to put parentheses where the 0 was, we would have to write it in this other form. But you want to try to steer away from doing that if you can. Okay, let's look at a cubic application problem. This is a box problem. We've seen something similar to this before. Suppose you want to make a box out of a square piece of cardboard that's 15 by 15 inches square. Write a function for the volume of the box if x is the length of the square that's cut out. So here are those squares that are getting cut out. Each side is x. So you can label them here. And then remember, we've got these kind of fold lines here. We would fold here, 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 and here. It would create this box without a lid on it. To find the volume, remember we're doing length times width times height. So length across is originally 15 inches minus my 2x's. So I'm just going to put 15 minus 2x. And then your width in this problem is the same because it's a square. So you can write it out twice, or you can just say squared. And then the height of the box is just going to be the depth of it, which is whatever your square cutout is. So that's just x. And there's my function. Use this equation to find the values that make the volume greater than or equal to 0. So the volume positive. Now, this is already in factored form, this equation we've written. So I can set my factors equal to 0. And solving the first one, I'll have -2x equals -15. And if I divide by -2, I'm going to get just 7.5, which we would probably say 7.5 inches rather than 15 inches because this is a real life situation. And then, of course, 0. So those are my breaking points, 0 and 7.5. You can plug values in. Say I plugged in -1, 1, and 8. We can do that in our calculator. If I plugged -1 into my function, it'd be 15 minus 2 times -1, and both of those parentheses squared, times -1. I get -289. If I plugged in +1, I get 169. And if you didn't catch what I did there, I just hit second, enter, and that's bringing up the last thing I typed in for me to be able to edit. If you want a little shortcut instead of typing everything in. So I get, let's see, negative, positive, and positive. Okay, so let's put those on our number line, negative, positive, positive. So the values that would make my volume greater than 0 or positive are between 0 and 7.5, and then anything greater than 7.5. Now, if you remember doing a problem like this before, there's actually constraints on the problem as well that go along with what it can actually happen in our cutout here. If we look at 0 and 7.5, if I cut out a square that x represents the size of that square, remember that's 0 by 0, that means I wouldn't have a cutout at all, so we would just have a flat box. And if I cut out a square that was 7.5 by 7.5, that would be 1/4 of the box, and if I cut out 4 of those, I wouldn't have anything left. So we can't actually have anything greater than 7.5 because I don't have any cardboard to be able to make those cutouts. My box isn't big enough. So the only solutions that make my volume greater than or equal to 0 are between 0 and 7.5. What are the max volume dimensions of this box? So let's look at that. We're going to put our equation in y equals, and we're going to calculate maximum. Again, we did something similar in a previous lesson. So 15 minus 2x, quantity squared, times x. And I'm going to change my window a little bit because I don't think I'm going to be able to see a very nice picture of this. So my x min, I'm going to make 0. My x max, I know it can't go past 7.5, so I'm going to say 8. X scale, I'll leave it 1. Y's here represent volume, so I'm going to say minimum volume 0, maximum volume maybe 500. It could be bigger than that. We'll see. Hit graph. Okay, and there's my nice picture. I want to calculate a maximum. Second, calculate. This time maximum is number 4. And we know it's somewhere between 0 and 7.5. So that's what I'm going to use for my left bound and my right bound. Left bound 0, right bound 7.5. And guess. And I get, it looks like about 2.5 and 250 is the maximum point. So let's talk about what that represents. 2.5 is the cutout, and 250 is the volume. So the maximum volume is 250, and I would say, don't forget it would be inches cubed if you had to label that. Now, the dimensions of the box are what we're being asked for here. So imagine that you cut out a 2.5 inch square from each side. 2.5, cross out my x's, and say I cut out a 2.5 square here. So that side of the box would be, instead of 15, minus 2.5, minus 2.5, it would be 10. And it would be the same up and down as well, because remember, this was a square. So the dimensions of the box are 10 inches by 10 inches by 2.5 inches, because 2.5 was the x value, or the height. And these values too you can get just by plugging 2.5 into this part of your equation. 15 minus 2 times 2.5 would give you that as well. You can double check that all three of these dimensions, 10 times 2.5, multiply to that volume, because remember, length, width, and height multiply together to get our volume. That's where we got that equation from. Okay, here are a couple practice problems for you. There's 2 of them here, and I'm going to kind of walk you through them real quick. So problem number 1 says the revenue for the sale of a product is given by the following function. Use factoring to find the number of units that will give a 0 revenue. So those are going to be your breaking points that you're finding in part A. And then part B, use your sign chart with your number line to determine when it's going to be greater than 0. So you can use the breaking points, plug in your test values, and figure out when it's greater than 0. Number 2, assume that there is profit when T units are sold, when T is greater than 0. And we're going to say P of T, profit, is determined by T squared minus 32T plus 247. For what values of T will there be a loss? Okay, and so for a loss, we want to know when our profit is less than 0. If our profit's equal to 0, we haven't gained anything, we haven't lost anything. If our profit's greater than 0, that means we've made some money. And if there's a loss, it means our profit is less than 0. Keep in mind here, this problem brings up a good point. T units, T represents a number of units, so we can't have a negative number of units. That wouldn't make sense. So whatever you get for breaking points, even if that makes sense algebraically, mathematically, your answers should only be positive numbers. And then same thing with number 1 there as well. If X represents a number of units sold, your answer should only be either 0 or positive numbers. Okay, so to find when we have a 0 revenue, we're going to set it equal to 0. And we're going to factor. These terms have something in common. I can factor out an x from each of them. And then I can set each of my factors equal to 0. If I set x equal to 0, we just get 0. If I set 49 minus x squared equal to 0, you can solve using your root method from before. Subtract 49, so negative x squared equals negative 49. Divide by negative 1, get x squared equals 49, and then take the square root of both sides, x equals plus or minus 7. And remember here, we can't have a negative number of units, so either 0 units or 7 units would make sense in this situation. Use a sign chart to determine the number that are sold that make our revenue greater than 0. So 0 and 7 are the breaking points that we're concerned about. We're not even going to worry about anything less than 0 because we can't have a number of units that are less than 0. You should have plugged numbers in like 1 and 8, for example, would have been good choices here. If you plug in 1, you will get a positive number, or 2 or 3 or 4 or 5, anything in that interval. If you plug in something larger than 7, you're going to get a negative number. So the number of units that must be sold to have a revenue greater than 0 are between 0 and 7. Strictly between, not equal to, because we don't want to have a 0 revenue, we want to have something greater than a 0 revenue, so only positive. Okay, let's look at question number 2. Here we wanted our profit to be less than 0 for it to be a loss, so we'll say P of T is equal to, actually instead of rewriting that whole thing, let's just say that function is our profit function here. So t squared minus 32t plus 247, that calculates the profit, and we want it to be less than 0 to show a loss. This one, hopefully you guys figured out, is factorable. If you didn't see the factors, you could have used the quadratic formula. Two numbers that multiply to 247 and add to negative 32 are negative 13 and negative 19. And that means if I set each of those equal to 0, we'll get 13 and 19. So those are the break-even points. That will give a profit of exactly 0 in this function. So we're going to put 13 and 19 on our number line. And remember, we can't have anything less than 0 for units sold, so we're not concerned about that. Here, if you plugged in 1, you would end up with a positive number. If you plugged in something like, I don't know, 15, 16, something between 13 and 19, you would end up with a negative number. And then if you plugged in something larger than 19, like 20, you would end up with a positive number. So if we want a loss, values less than 0, anything between 13 and 19 would make that happen. And again, strictly between them, not equal to them, because if they sell exactly 13 units or exactly 19 units, that's when they would break even. Okay, let's look at a quartic problem. Let's make it a little bit bigger now. So I'm going to get it equal to 0 or compared to 0. So I'm going to move my 16 over to the left to start. X to the 4th minus 16 less than or equal to 0. And then I'm going to factor this. This is an example of difference of squares. Two things that I can take the square root of, and they'll factor into conjugates, 1 plus and 1 minus. If I take the square root of x to the 4th, I get x squared. X squared times itself gives me x to the 4th, if you want to think of it that way. What times itself gives me 16? 4 and 4. And now both of those, if I set them equal to 0, we can get our breaking points. On the left, if I subtract 4, I get negative 4. And then if I take the square root, I get an imaginary number, because there would be a negative under my square root. So we're not going to actually get any breaking points that are real numbers from that problem. That part of the problem, I should say. For the other one, I'm going to add 4 and then take the square root because it's an even root. Don't forget your plus or minus. So positive and negative 2 are my breaking points. Negative 2 and positive 2. And when we plug our numbers in, remember we're plugging them in here where my equation or my inequality is less than or equal to 0. So here also we want to think about we're looking for negative values. That's where our solution set's going to be, and the values that are equal at 0. Let's say I plugged in like negative 3, for example. Negative 3 to the 4th would be a positive 81 minus 16. That would give me a positive number. If I plugged in 0, I would have 0 to the 4th minus 16, which is negative 16. That's negative. And then if I plug in 2, well, actually 3, I've needed a number a little bigger than that. 3 to the 4th would give me 81 minus 16 would also give me a positive number. If I want values here that are less than or equal to 0, again, those negatives are what we're looking for. We do include our breaking points because our inequality was equal to. So we say our solution set is negative 2 to positive 2, inclusive with the brackets on either side. And then remember, you could always write that in inequality notation like so. Inequalities are always pointing at the same smaller number in the same direction. Okay, if you see a quartic function, you may also see something like this, where it can be factored by grouping. We reviewed grouping a little bit earlier, but that was where we had to create our own grouping situation. So we're going to do this one now. So we're going to pair up our values 2 and 2 and factor out what they have in common. The first pair of numbers have an x to the 3rd in common, and that leaves me with an x minus 8. The next pair of numbers have an x in common that I could factor out, and maybe let's factor a negative x out, so then I'm also left with x minus 8. Remember, we want that same factor both times. So now x to the 3rd minus x and x minus 8. Now it looks like we can actually do a little bit more factoring. Both of these terms have an x in common. So I'll take an x out, and that leaves me with x squared minus 1. And now this is something I can set all my factors equal to 0. If I set x equal to 0, I get 0. Easy as that. If I set x squared minus 1 equal to 0, I would have to add 1. And then take the square root of both sides. Square root of 1 is 1. Don't forget your plus and minus. And if I set x minus 8 equal to 0, I get x equals 8. So let's set up our number line here. And just be careful when you get a lot of numbers, you want to make sure you put them in the right place in the number line. So let's see, negative 1, 0, 1, and 8 are what we're looking for here. Now, once we have all of those, you can use your test points. And I'm going to show you a little trick on this one with the graphing calculator because it does get a little tedious to plug those numbers in. So in your graphing calculator, let's put our function in. X to the 4th, let's clear that out. X to the 4th minus 8x to the 3rd minus x squared plus 8x. And then instead of going to the graph, I'm going to go to the table of values. So I'm going to hit second graph. And then you can easily see what x values will give you certain numbers. And this is a good way to check your breaking points too. You can see -1, 0, 1, and if I scroll down to 8, those would all have y values of 0. So those are your breaking points. All the values less than -1 are positive values you can see here. So I can just put a plus there. And then all the values between 1 and 8 are negative, and all the values greater than 8 are positive. So I'm going to fill those in my number line. I'll use a different color here. So what did I say those were? Between 1 and 8 were negative, and this guy was positive, and this guy was positive. Now the only bad thing about the calculator is you can't see half values, which we need here because -1, 1, and 0 are really close to each other. So you can change how your table counts by hitting second window, and then table start. That can be anything. I just like to always reset mine to 0. That's the first number you'll see. And then the triangle TBL means change in the table. So that's how often you're going to see a value, what it's going to count by in your table. So I'm going to use 0.5. So again, to get to that, I hit second window, and then table start, always just put a 0. Triangle TBL, that's what it counts by. The default is 1, which all your calculators were probably at. So now if you hit second graph again, you'll see all the half values as well. And we want to focus in on -1/2 and +1/2. -1/2 gives me a negative number, and +1/2 gives me a positive number. So let's fill those in, negative, positive. So that just saves you a little bit of time with all those pluses and minuses if you don't want to plug the values in by hand or you don't feel like you're doing it right. Okay, here we're looking for where my inequality is greater than or equal to 0. So those are my positives, and we also want to include our breaking points. So my answer in interval notation is -∞ to -1 with a bracket, 0 to 1 with brackets, and 8 to infinity. Here's one for you to try on your own. I'll give you a little hint to start. Instead of factoring the x out later like I did, you might want to start by factoring the x out at the beginning here. All right, go ahead and try it. All right, so if I factor an x out, that's a 6x to the third, a 4x squared, a 3x, and a 2. I'm going to factor what each pair have in common. I'm just going to leave that x hanging out there for a minute right now. The first two have an x squared in common and a 2. If I take that out, I'll be left with 3x plus 2. The next pair of numbers don't have anything in common, so just a +1. 3x plus 2 would be left. And then if I condense all that together, I'd have 2x squared plus 1 and 3x plus 2. And then don't forget that x we factored out at the beginning. So this is your factored form of your inequality. I'm going to set each factor equal to 0. Okay, and in the middle one, if I try to solve using my square roots, if I move that 1 over, I get equals -1. X squared equals, divide by 2 would be -1/2. And if I take the square root, I'm going to get an imaginary number. So again, that's not going to give us any answers or any breaking points. Here, you get -2/3 if you solve for x. You only have 2 breaking points in this problem, 0 and -2/3. And you can use your table if you want to figure this out kind of quickly. Let me put it in my y equals. So we're just going to change this to 6x to the 4th plus 4x to the 3rd plus 3x squared plus 2x. And then I'm going to go straight to my table. And I want a number smaller than -2/3, so -1, -2, any of those. You can see it's positive. A number between -2/3 and 0 would be -1/2. That guy's negative. And then anything bigger than 0 is positive. So your signs in your number line should be positive, negative, positive. In this problem, you're looking for the values that are less than 0. So negatives, because it's strictly just less than 0, we do not include the breaking points. So your final answer here is -2/3 to 0 in interval notation. Okay, our very last problem, this problem actually comes from my math lab. I wanted to do an example of it because the notation's a little iffy with it. So it says, use the graph below. We've got two functions graphed here. The blue one is function f of x and the red one is function g of x. We want to determine values for x where one function is less than the other or greater than the other. So here we want to know where function f of x, which I'll write blue, is less than g of x, which is red. So this is a fancy way of saying when is the blue below the red. So where they're equal or where they're intersecting, here and here, and the part of the graph where the blue values are less than or lower than the red graph are here. Okay. Now we are listing the x values where that occurs. The x value where they are intersecting are at -1 right here, and at +3 here. So anywhere between -1 and +3, the blue graph is below the red graph. So we would say our answer in interval notation is -1 to 3, and because my inequality symbol is not equal to, it's just less than, we would use parentheses. You may also need to put it in the other notation in your homework. -1 to 3, inequality symbols point in the same direction at the smaller number. Now, if we look at the other part of this problem, we want to know when is the blue graph greater than or equal to, so above the red graph. So that would be here and here, which are pretty much every other part of the graph except the numbers between -1 and 3. So those values are -infinity to -1 and 3 to infinity. And this time, because my inequality symbol was equal to, we would use a bracket. Now, if I put that in the other notation, it would be all x values less than or equal to -1, and also all x values greater than or equal to 3 would be how we would write that. Okay, so if you see this notation with several graphs, try to translate it. Use the colors to help be helpful here. If you see less than, think below. If you see greater than or equal to, or just greater than in general, you can think above.